Okay, everybody, good morning. Today we're doing 5-6 uninhibited and inhibited growth and decay models. Nicely, this is a short lesson. There's only 6 slides, so it should go fairly quickly. Okay, so we are going to assume that a colony of bacteria grows at a rate proportional to the number of bacteria present. If the number of bacteria doubles in 5 hours, how long will it take for the number of bacteria to triple? So if you want to look back through your book, I tried to make this simple and quick. So it's going to follow this, this model where K is a constant and N of T is the number of bacteria present at T time. Or time t. Okay, so my N of t follows a growth model, which you may remember this from Algebra 2, Trig Pre-Calc, e to the kt, where N naught is your initial bacteria, t is your time, and k is your growth constant. Okay, so we can use the fact from what they just gave us is that after 5 hours, so N of 5 is going to equal 2 N naught because they told me that it was going to double after 5 hours. Okay, so let's just go through the math here. So N of 5 is equal to N naught. Sorry, we're using our equation, the e k to the t. It's e to the 5k, and that's going to be equal to double my initial value. So if I divide both sides by N naught, I get e to the 5k is equal to 2. Then I'm going to take the natural log of both sides. So now I'm going to have 5k is equal to the natural log of 2. If I divide both sides by 5, I get k is equal to 1/5 the natural log of 2. Okay, so now I've got kind of this general equation, and they want to know how long it's going to take for my bacteria to triple. All right, so now we're trying to figure out our N of T, but I don't know what I'm looking at, right? My general equation is N naught e to the, I now know my K, which is 1/5 natural log of 2. That gets multiplied times T, and that is going to be equal to 3 N naught because I'm trying to figure out how long it's going to take for it to triple. Okay, so nicely when I divide both sides by N naught, I just get e to the 1/5 natural log of 2t is equal to 3. Again, I'm going to take the natural log of both sides. So now I've got 1/5 natural log of 2t is equal to the natural log of 3. So if I multiply by 5 and divide by natural log of 2, t will be equal to 5 natural log of 3 divided by the natural log of 2. And I did that math, and it is about 8. So my bacteria will triple in approximately 8 hours. Okay. All right, so for a radioactive substance, my rate of decay is what we just talked about. I just gave you a little bit of preview on that. So remember that a half-life is used a lot for decay, right? So let's see what that looks like. Okay, so the skull of an animal found in an archaeological dig contains about 20% of the original amount of carbon. If the half-life of the carbon-14 is 5,730 years, how long ago did the animal die? So they're giving me information so that I can find the constant for my half-life. So if I have A is equal to A of t, it's going to satisfy this equation. Okay, so the solution for that is going to be just like our other one, A naught e to the kt. Okay, so then to find my half-life, I'm going to have 1/2 A naught is equal to, my A naught, E, I'm looking for K. They're telling me that my T is 5,730 years ago, and now it's just a little bit of math. Divide by A naught, I get 1/2 is equal to E 5730K. Take my natural log of both sides. So then I get the natural log of 1/2, or 2 to the negative 1, is equal to 5730K. Then if I divide by that, I can bring this negative down because it's a logarithm. So I get a negative natural log of 2 divided by 5730, and that is my K. Getting rid of that 1/2 and making it a negative natural log of 2 is just an easier way to deal with it. So now they asked me how long, or I'm sorry, that there's 20% left. So I've got 0.20 A naught, because I have 20% left, is equal to my A naught E. Now I know my K, which is negative natural log of 2 divided by 5730. Remember, this is all in the exponent. It doesn't look like it very much, though. Here, let me try to fix that. So now my A naught looks weird. Sorry. There. And then I've got my T, right? So now it's just a matter of solving. So I'm going to divide both sides by A naught. I'm going to have 0.2 is equal to E to the negative natural log of 2 divided by 5730T. Then of course, I'm going to take the natural log of both sides. So now I have the natural log of 0.2 is equal to a negative natural log of 2 divided by 5730T. If I multiply both sides by the reciprocal, okay, so then I'm going to have my T is equal to 5730. We can put the negative up top, natural log of 2 divided by, natural log of 0.2. Kind of lost my 0.2 there. Okay, you do that math, put it in your calculator. My time is approximately 13,300 years. So what that tells me, because there was 20% carbon left, this animal died. Forget what the animal was already. Oh, it just said the skull. All right, so an animal, it died approximately 13,300 years ago. Okay? All right. Okay, so now we're solving differential equations involving inhibited growth and decay. So you guys can read all this. I'm not going to read it to you. These are our models. The thing that you need to recognize is that you have limits. So it's going to approach some limit that it doesn't go above when it's growing, and it's going to hit some limit that it doesn't go below when it's decaying. So that's just how it works, because things don't grow without bound. Like bacteria, they run out of food, they whatever, let's hope with the coronavirus, right? Newton's law of cooling is a great example of an inhibited decay model, so we're going to do one of those real quick. So this problem I can solve for u very easily, because then I get u naught minus t e to the kt plus t, okay? So then this just becomes u of t, little t. Big T is temperature, little t is time. Let me just copy this. And then, of course, K is my constant. So the T that's inside, well, actually, they give us enough information up here that we can just plug stuff in, okay? So my U of T is 60 because they're saying that if after 10 minutes the temperature of the object is 60, then I know that this is 60. Then my initial temperature is 90. The surrounding temperature is 20. And did they give me a time? 10 minutes. So that is going to be 10 because this is in terms of minutes. And then plus 20 because that's my ambient temperature, my T. So if I subtract the 20, I get 40 is equal to 70 e to the 10t. Divide by 70, I'm just going to get 4/7 because the zeros cancel, e to the 10t. Take the natural log of both sides. Here, maybe I'll do this so that it makes sense when you look at this later. Okay. All right, so then I've got the natural log of 4/7, oops, not 47, is equal to 10t. So I would divide by 10, so that just becomes 1/10. Natural log of 4/7 is equal to t. Nicely, I can rewrite 1/10 as 0.10. Natural log of 4/7. Oh, that's not t, it's k. Dang it. Sorry, you guys. We're okay, I paused us there for a minute so I could go back. 10 was the time that I put in so that I could solve for k. So I just went back through and fixed all these. Okay. Now, you may be wondering why I'm leaving these things in terms of natural log, because it's pretty complicated looking. It's because it's the most accurate solution. And if I round now, I could get a big rounding error later. So our general equation becomes u of t is equal to my u naught minus t e to the k, which I now know is 0.10 natural log of 4/7, times my T plus my big T, which is the ambient temperature. Okay? So now they want to know what's happening after 20 minutes. So that is just going to be a U of 20, and then all my other information stays the same, right? My initial temperature was still, I think it was 90 up here. 90, my ambient's still 20, so it's going to be 90 minus 20, which will just be that 70 that we found earlier, e to the 0.10 not 4/7, natural log of 4/7. Natural log 4/7 t plus 20, I believe it was. Okay. So then now it's just doing math, right? But I know my T is 20, so I can plug that in up here. So I'm going to have 70. E to the 20 times 0.10 is going to be 2. Natural log of 4/7 plus 20. If I just plug all that into my calculator, I find that the temperature will be approximately 42.86 degrees Celsius. Okay. All right, I hope that makes sense. If you guys are struggling, please remember you can text, email me, whatever. Happy spring break. Homework is not too bad. So we are looking at pages 450 to 453. And I tried to be nice, 1 through 17 odd. And then the odd AP problems, but there's only 2. So you're just doing 1 and 3. So that gives you a total of 11 problems. All right, I miss you guys. Happy spring break.